Should we start? Yeah. So, hi everyone. Today we have Pablo from Strathclyde talking about this crossover between collective dynamics and scrambling sparse models. So let's go ahead.
All right. Very much, Jay. And yeah, thank you for the invitation. It's really a pleasure to come here to visit for the first time, and I'm a real fan of the format of visiting for 1 or 2 days, giving a talk, and just having physics conversations all the time. I think that's something that I wish I get to do more frequently in Strathclyde in the future. And it's great to hear about all the research that goes on here. So I'm going to be telling you about some newer results which are connected to this idea of collective dynamics and scrambling and sort of kind of connecting or building a bridge between them. And they are based on these sparse models, which you might have heard about given some of the connections with Strathclyde, but I'll tell you more about that. Right, so I'll just dive into the topic. I'll mention some of my other kind of research interests and projects at the end, since if we have some more time, I'm very keen to discuss about other topics today or tomorrow as well. All right. So the topic of the talk or the main setting is spin systems with long-range interactions and trying to understand a bit, what kind of interesting things we can see in those sort of systems from different point of views. You can argue that there's a big kind of surge in interest on these systems from the past 2 decades, because many of the leading quantum information processing platforms kind of naturally seem to implement these long-range interactions. The case of cavity QED, where interactions are mediated by light, it's an example of this, where you can, in a sense, go beyond the usual connectivity rules that we think of in condensed matter models. Read-there atoms also present long-range interactions, and you can have very particular sort of dynamical regimes. And trapped ions, sort of in a similar way as cavity QED, you can have interactions that are mediated by some other physical degree of freedom that allow you to connect beyond just the local geometry of the system. And so 2 things that in principle might come to mind that you can achieve with spin system with long-range interactions are the following. So the first one is what I'm going to call collective dynamics. You could call this in a variety of ways, depending on kind of where you come from. So the idea in these cases is that there are certain systems, if you have very long-range interactions and the system is very symmetric, then mean field becomes a very good description, and you can describe the dynamics of the model in terms of collective variables. So this J, which of course I didn't define in the first slide, is like the sum of all the spins of the system. The entanglement that you generate in this sort of dynamics when you start with an entangled state is very particular. So you get, for example, this sort of spin squeezing state, which is sort of in the boundary between being a classical and a non-classical state. But it has entanglement. It's very useful for example, quantum sensing. And these sort of systems and these sort of states, even though they are kind of a limit that is not usually implemented in experiments, is a very important, or gives us very important toy models for studying states for quantum sensing. And kind of on the flip side of that, there's this issue of scrambling. So the idea that, if you want to think about how information propagates on the different degrees of freedom of a system, if you have long-range interactions, this allows you to have a faster propagation of the dynamics. So this is a particular flavor of quantum chaos or quantum chaotic dynamics, in which operators grow extensively very fast. And it's, in some sense, roughly speaking, very quantum complex. It's very hard to simulate classically, perhaps as opposed to the collective dynamics, which admits this mean field description. So the most exaggerated example of these things can be seen in all-to-all spin systems. So all-to-all is a very strong form of long-range interaction where there is no form of geometric locality whatsoever. All particles see each other. There are these very nice clean toy models where you have permutation symmetric models. For example, the one that I've written here is a all-to-all symmetric Ising model in a transverse field, which is also called the LMC model. So again, when you have this sort of strong permutational symmetry, you can write everything in terms of the collective operators, which I've now defined here. And you get, for example, in the case of this spin squeezing dynamics, you get exactly those sort of states. The Hilbert space is very restricted because these Hamiltonians commute with the total spin of the system. So if you start with a state with a definite J, so J being the total spin, you're going to stay there. And so you start with a symmetric state that's also a state of maximal J. And so that really restricts your dynamics to a Hilbert space that is linear in the number of particles. But the generation of bipartite entanglement is greatly constrained in these sort of systems. And so you typically, because the Hilbert space is not as large, the states that have the maximum bipartite entanglement in these subspaces have entanglement entropy scaling as log n. And as I said before, the mean field description is exactly the thermodynamic limit, and this means that any Hamiltonian that you write in terms of collective variables is integrable, so you can't have chaos. You can have chaos if you are driving, but we are not going to talk about that. And then, again, on the flip side, random all-to-all models, I wrote this kind of all-to-all spin model, which is sort of a Sherrington-Fitzpatrick model, but you could think of, because the title of the slide was spin systems, I didn't want to write the SYK. But again, having broken explicitly the permutation symmetry, you get a very different sort of behavior. You enable this fast scrambling. So, the time, I'll define this, more in detail after, but, the time that basically takes for information to reach all the degrees of freedom scales of the logarithmic of n. This is highly quantum chaotic. You expect your dynamics, if you start from a product state, to kind of equilibrate and generate an entanglement of the order n. So what I'm trying to just paint a picture of is that, with these all-to-all spin systems, clearly by changing the sort of interaction, you can have very different behavior. Which in a sense is like the opposite. So what I want to discuss today is some results in which we try to study a sort of crossover between the two behaviors in these kind of very densely connected spin models. And so, if you've seen, or if you see these slides as I'm telling you about it, you could think, well, I could, if on one hand I have all the couplings are equal to 1, and on the other hand they are all random, well, I could devise a way to interpolate these two models between each other, and then I'll have the collective behavior on one end and the scrambling behavior on the other, and that could be one way of doing things. But what I'm going to talk about is actually a situation in which I have a fixed model. And this fixed model has no free parameters and has no random. So it's a deterministic model. And so I'm going to describe how you can see this crossover between these two behaviors in this fixed model. And this model, which I'm going to tell you a bit more about later, is not all-to-all, but it's what we call a sparse model. So it's a model that you could think of it in 1D, so a 1D chain or a 1D ring, where I don't have all-to-all interactions, but instead I have a sparse graph of interactions. Okay, so that means, as you'll see, that the number of couplings at each given site scales as the logarithmic, as the log of n, instead of n, which would be for an all-to-all model. So we're going to focus on this kind of x models on these coupling graphs. And there has been some work mostly related to our group or Andrew's group, let's say. It really all started with well, I guess this is from later, but this was a proposal by Monica Schreier-Smith to implement these sparse coupling graphs with atoms in optical cavities. And so there was kind of a search of theoretical interest in trying to understand what these models could give you. And so these are some references from the last couple of years. And so the idea is that we are not going to be changing the model, as I said. We're going to be changing actually the initial state. So I have a fixed model, and I'm going to show you some results about what happens if instead of starting with a collective state, which is this state, so this is the state that would generate this in squeezing if I had an all-to-all coupling graph. So this will stay on the collective side of the line here, but I'm going to start flipping spins in my initial state, and then I'm going to see what happens if I flip half of the spins. What sort of behavior do I get? So my control parameter, in some sense, it's just going to be the initial state.
So will this model have certain symmetries?
Yes, well, I mean, it has the U1 symmetry and the coupling graph is, I mean, it's you think about this graph, but with periodic boundary conditions on a ring. So yeah, so it's a translation invariant system.
Okay.
So you only care about the difference between I and J in your
Yes, absolutely. Yes, this is the most general case because of what I'm going to show you in the next one, but definitely this chi-ij in probably all the results that I'm going to show is a translation invariant graph. All right. So one way that to think about this sparse coupling graph, why would you even think about this sort of connectivity? So I mentioned there was kind of a proposal originally to do this with atoms in optical cavities, but you could also think about these models as kind of inspired by a technological breakthrough, I would say, which is that you could, in these experiments with neutral atoms in Twister arrays, you can actually coherently change the position of the atoms during the execution of, say, an algorithm. And that algorithm could be, the time evolution or the trotterization of the time evolution of your Hamiltonian. And this was, I don't know when it was first demonstrated, but perhaps one of the main or the most important demonstrations was back in 2024, where the Harvard team started building these neutral atom quantum processors in which you had different zones. And so you will move your atoms to an entangling zone, which is illuminated by an entangling laser when you wanted to entangle them. If you don't want to do anything, you keep them in the storage zone. And if you want to read out, you move it. So, and you can do so, as long as, so in this platform, they have very, very long-lived coherence as long as these are hyperfine qubits. Anyway, so that's the experimental connection. So how does it relate to sparse coupling graphs? Well, for example, you can think about the following protocol. So suppose I have a chain of n spins or n atoms, and I take n to be a power of 2, right? So here, this is 2 to the m, where m is 3. And I think I'll doing the nearest neighbor. I guess I do pairwise gates. According to some Hamiltonian, it doesn't really matter. The only thing that matters is the final connectivity. So I do pairwise gates, 0, 1, 2, 3, 4, 5, 6, 7. I turn it off. And then if I dream about having this power of moving the twisters, I fan them out, and then I can move the last 4 and intertwine them with the first. And this is called a Faro shuffle operation, which is what you do when you're shuffling cards. And then you do the same, you pairwise entangling gates. You can keep playing this game. And if you repeat this m times, then you're going to go back to the original layout. And what you've had generated is a coupling graph, which has the form of a hypercube, so an M-regular hypercube. And the number of couplings that the hypercube has basically scales, as I was saying. So it's n/2 times log n. So per site is log n. And so we're not going to, so on one dimension, like if I take a hypercube and I just, project it or just put all the particles in one dimension, that's not translation invariant. But you can define a model which basically is like the hypercube, but you fill the missing edges such that it's now translation invariant. And this is called the powers of 2 model. So the powers of 2 model is a model in which the coupling in the Hamiltonian is 1 if the distance between the particles is a power of 2. Okay? Where is 2 to the k, where k equals 0, 1 till log n. And it has the same property that the number of couplings per site is logarithmic. So this is what we call a sparse graph. Does that make sense?
That's not analytically solved.
What property? I mean, there are some things that you can.
I mean, a hypercube you can easily diagonalize. Ignore rotations and stuff.
To obtain what? You mean the xy Hamiltonian in the hypercube?
Yeah. If you put xy on this thing, it's not.
I don't think. I see what you mean. I don't think you can solve it exactly. So one of the papers that I mentioned before from one of Andrew's students, they characterize the phase diagram of the powers of 2 model. But it's not XY now that I think about it. That's a transverse field one, which is a different case. I don't know. I'll have to think about it.
So it's a scalar.
Yes.
Then you can't.
But the hypercube is also chaotic in the zero magnetization sector.
Okay. So then I don't understand what you mean by hypercube. Is it XY model?
Yes.
Oh, it's XY.
Yeah.
You're thinking of like you have.
I'm thinking of sum over X. That's also a hypercube.
But you're thinking of what? Sorry.
Sum over X.
If you just think of like second basis states, that's like a hypercube.
I see. So this is. Well, I guess I should have it here. Yeah. So this is this with xyj being, well, I mean, in this case, the powers of 2, but it could be.
So like when you use experimentally, is it easy to make this delta t small? So, or is it like a flow case system in practice where?
So again, there are 2 ways of implementing this in principle. The one with the shuffling, yeah, I mean, I guess easy is relative, right? The problem with doing that is that the XY interaction is complicated to do. So it's kind of a long winding story. But so Rydberg atoms actually have native spin flip interaction from the van der Waals interaction. The problem is that you get that if you encode your qubit in like one of the hyperfine states and the Rydberg state. So that's your 2-level system. The problem is that the Rydberg state is not trappable. So you cannot have the traps, the tweezers turned on if there's a chance that the atom is in the Rydberg state, because it's actually anti-trapped. And so the way to move atoms, as I was saying before, is to have atoms in the, like information encoded in the hyperfine. Information encoded in the hyperfine, what's most natural to do is icing. So you need to throttlerize that into icing. And we studied that in the paper. I'll show you the paper. I'm not showing results of that. Yeah. The other proposal with the atoms in cavities, you don't need to shuffle anything. So in principle, that has been actually demonstrated, but it has other problems. Okay, so this is then I've drawn here the adjacency graph, right? So the adjacency matrix, sorry, this xij or chi ij, sorry. for the powers of 2 graph, I think for 32 particles, just to show you that, you know, this is then in fact, this is distance 8. And then you have these other couplings that start appearing because it's periodic. So coming back to what I was telling you before about, you know, people who have studied these models before. So this was first kind of introduced as a deterministic alternative to like random spin networks. One in which you don't have all-to-all interactions, but you can still prove that you have this fast scrambling. So you still have a scrambling time that scales as log n. And so this was this paper right here, where basically what they study here is the initial states are random states on the equator, right? So they are very non-collective. So in a sense, they are an analog of a maximally or infinite temperature state. And in this, sorry. Okay, hopefully you can hear me and see the slides again. Great. And so in this kind of original work, what they showed is, you know, in this, if you have this model and you look at these sort of infinite temperature states, you can, well, they studied a number of things, but one of the things that they do that I'm going to touch upon later is this classical sensitivity, which is you can take a semiclassical limit of the model, which I'll tell you in a bit, but you can calculate like a classical analog of the OTOC, which is just trajectories of, you know, a given spin to a perturbation in some other site. A tiny perturbation, you know, I do a small rotation A, and I look at how that affects like J in terms of the magnetization, and I look at that has kind of the flavor of an OTOC. What they showed here is that, you know, that this graph displays you know, an exponential increase of this quantity, and you can, and they show that the time that it takes for this quantity to become 1, basically, so it starts very small to become 1 scales as log n. So this is the scrambling end of the analysis. Then we have the other end of the analysis, which we did a few years ago, which is now we think our initial state that is collected. So all spins pointing along some direction in the equator, but a fixed one. So again, just for reference, I'm going to show you briefly what happens in the case of all-to-all, just to remind you. So if I had an all-to-all permutation invariant graph, Hamiltonian, you can, as I was saying before, you can write it in terms of collective spin operators, and this is what you call the one-axis twisting. So it's just the collective z squared. So it's kind of a nonlinear rotation around the z-axis. And the dynamics of the perfectly all-to-all Hamiltonian, of course, is analytically solvable and has been studied for a long time. And one of the things that you see is that if you study the quantum Fisher information associated with the time evolved state, then you get curves like this, where you have you know, a ramp, then a long plateau, and then a peak. And at the peak, what you're reaching is a GAC state. So these models generate dynamically GAC states. And what this plot is kind of meant to show is that this is the quantum Fisher information density. So this scales linearly with the number of particles, meaning that you know, all these curves have Fisher information scaling quadratically, which is this Heisenberg's scaled feature information. Yes, absolutely. So this is all-to-all. Exactly, just to remind what you would expect. But if you now do the powers of 2, so it's exactly the same as before. This model is chaotic, okay? But you're starting with this particular initial state, or this family of initial states. What you find is that you get actually a very good tracking of the, what you would expect from the all-to-all dynamics. Okay, so basically I'm plotting the same thing here, quantum information density, quantum feature information density versus time for now these powers of 2 coupling graph. And if you look, I think this plot is looking at the value at the peak, which should be very close to a GAC state if that's actually what you're getting. Basically showing that up to the size that we simulated, it basically tracks the all-to-all very well. Okay, so what this is saying is that for this problem, right? So this is what we want to understand in some sense. For this problem, this powers of 2 model has enough connectivity to mimic all-to-all. Okay, it clearly cannot be all-to-all because of all the things that we said before, among others that this, this one is integrable and this, right? But we are going to, the idea will be to reveal these different signatures of the dynamics by changing the initial state. Okay. Yes.
Is there an advantage in like the time which this information is?
Not really, because I mean, it depends on how you normalize things in a way, but the all-to-all always has more terms in the Hamiltonian, right? So yeah, it's faster. But yeah, I think you could do some sort of physical argument of how easy it is to have n squared terms in the Hamiltonian versus n log n. Here, everything is rescaled such that this curve looks like this one. But the time that it takes is this. Anyway,
But maybe I'm missing something here, but the fact that this scales as n squared, I mean, a priori, does that have anything to do with chaos and scrambling? So
no, sorry. So this is meant to just illustrate. It's not meant to illustrate anything about chaos. If anything, it's meant to illustrate that you can have very non-chaotic behavior.
Yeah.
Chaotic dynamics should leave. I don't have plots here, but it typically, the feature information of a random state in the whole Hilbert space is order n, right? And this is generating something that's way beyond that. So if anything, this is showing dynamics which is very non-chaotic. If anything, it resembles an integral model. But what I want to emphasize is it's exactly the same model, but I changed the initial state.
can you tell us also in this last scaling plot, so there are different geometries?
Yeah, so here, so this is the all-to-all. This is the powers of 2. So the 3 that are on top of each other are all-to-all powers of 2 on the hypercube, which we did analyze for this problem. So a hypercube is a bit wonkier because it doesn't have this extra symmetry, but you get basically the same behavior, while this is just nearest neighbor. Your nearest neighbor, you start to see, I mean, the spin exchange interaction offers some sort of protection of the collective motion. I'll talk about that later. But if you don't have enough connectivity, it's just as you.
Because the graph becomes sparser, you won't get n squared.
It's a good question. You won't get n squared. I actually don't know. There's someone in Andrew's army is looking at that. Powers of 3 and generalizations, but I have to think about that. Maybe there's something that could be said, but I'll show you. I mean, this is empirical in a sense. I'm just doing the numerics and showing that it works. I'll show you an argument that you can scale to very large system sizes. All right. So then, as I was saying before, I was trying to emphasize that we changed the initial state, right, and changed the behavior and changed what kind of dynamics we were probing in the Hamiltonian. And so I'm going to do that now systematically, right? And in the way that I anticipated before. So again, I have this periodic powers of 2 model. S here is meant to represent the local spin. It was 1/2 for most of the cases that we talked about. And we're going to now start with different states, knowing that, if the state is this polarized state, then I will get the behavior that I showed you in the previous slide, because that's the state that we use. And if the state is kind of unpolarized, in 2 slides ago, I showed you one where each spin was aligned randomly on the equator. We expect that this unpolarized state will basically mimic that behavior. And so the way of connecting both of them is just flipping one spin at a time. Okay, and you can do that in a variety of ways, right? There's no only one way of introducing kind of a defect or a spin flip. And so I'll show you results for a couple of them. I'm not sure we understand completely what happens in every case, but we understand some of it. So this is kind of work in progress. So any thoughts and ideas are appreciated. So, okay, there's a lot going on here, but I'm trying to convey in a single figure what happens as you start doing these spin flips. So the colors are going to represent the number of flips we're doing, okay? With black being 0 flips and yellow being n/2, which is the maximum that we consider. And we're looking at 2 quantities, the quantum Fisher information density again, just to compare with what we had seen before, and the entanglement entropy, both at the half size entanglement entropy as a function of time. And so what do we see? Well, for 0 flips, of course, we knew what we get, right? These clear peaks in the Fisher information. And as we start flipping spins, you kind of still, you still have that behavior, which you have that peak, but the height of the peak starts becoming reduced. So that's important because it means that the Fisher information is smaller. And so and you keep doing that, and eventually, when you get to the yellow curves, then you start getting this behavior where this basically started at 0, but it's now equilibrating at something that's order n, right? Right, and if you see 2 curves here, is because one of them is doing one sort of flip and the other one is doing other sort of flip. For entanglement entropy, we have kind of the opposite behavior where entanglement for the 0 flips, it's almost periodic because the dynamics is actually almost periodic. And it has these very large temporal fluctuations. And then the mean value is set at a relatively small value if you take the mean over the fluctuations. But if you start flipping spins, then what you see is that the fluctuations start to disappear, the entanglement entropy starts growing, and eventually it looks like an equilibrated system, what you would expect from a chaotic system. So this gives us an idea of how these 2 regimes are connected. So I'll tell you a bit about how we've studied this a bit more systematically. So of course we are very constrained with system size because this powers of 2 model is kind of annoying that really you want to study values of n that are powers of 2 because otherwise you don't have the same number of edges. I mean, you could still do it. And so I'm going to show you a few tricks to get around that.
So is there anything unexpected?
No, I mean, it's, I don't know. I mean, unexpected is very subjective, right? I mean, it shows that you have kind of a continuous interpolation of the 2 regimes. That adding a single, I mean, it could still happen if I had a very large system. I don't remember. I think this is n equals 16, probably. Yeah, it's n equals 16. If you had a very large system, things could be different, but it wasn't clear to me at least what would happen if you include a defect on your initial state and you break the symmetry manifestly, because there you've broken the gravitational symmetry of the initial state. What would happen to the Fisher information? Would it plummet down, right? Or, well, in this case, we see there's kind of a continuous change between periodicity fluctuations and high Fisher information and this kind of equilibration regime and high entanglement entropy.
Like the way the entropy is distributed, so this is telling you that you have states which generate a lot of entanglement, but the entanglement is like not multipartite, right?
Yeah.
So do you know like how the entanglement is distributed? Like is there some-
No, I don't think we haven't studied that. Yeah, that's a good question. But yeah, I mean that's definitely something that one could argue is happening here, but we haven't looked at the specific like microscopic distribution of entanglement. I mean, you could argue that this is a coarse grained picture of that question, right? I take two quantities that I know what they are measuring, and I look at them instead of looking at what happens inside. But yeah. All right. So we can go back to the sensitivity analysis that I mentioned before. So just saying a few more things about that, you can take this spin system, and now instead of saying, S is very small, like the local spin is 1/2, you can say S is actually very large. And you could define semiclassical or a classical system by just doing a mean field approximation. And so what you do what you get if you do that is just a set. It's a classical many body system. You have three, each degree of freedom has three variables, which are the spin components, but actually the spin is conserved for each spin, so you only get two. And so, but you solve it typically as a set of 3n coupled nonlinear ODEs. And you look at this average sensitivity, as I was saying before. So what you're interested in knowing is how the dynamics of the magnetization of a single spin at site J will react to a perturbation in site I. And so you can think about this as a kind of Poisson bracket of sort between the classical variables. So if you had chaotic motion, you would expect this to grow with the Lyapunov. And so I showed one case in some sense before, which was this case, which is the case where you've done a lot of flips. So this is n/2 flips. So this is way into the case where the initial state is completely disordered. But now I'm showing you kind of a different snapshot. So you can do it for n/4 spins, for example, just to show you an example, or even for 0 spins, which is the case that we have for collective behavior. And you can see that, particularly from this ones, there is a big difference in how the classical sensitivity behaves. Again, showing that the different initial states are probing different behavior. So the different curves here represent the graph distance. So the graph distance is basically how far away are I and J in the graph. Okay? Not in physical space, but in the graph. So it goes up to log n for each n. And what we look at is we look at two things. One is you think about the time that it takes for this sensitivity to reach order 1. We call that T star. And then with this exponential increase, we do a fit to calculate the Lyapunovs. So this is the classical system, so it allows you to do very large system size calculations. So this is what you get. So this is the Lyapunov exponent that we obtained from the fit for a particular way of flipping spins. But you get very similar things for other types of flips as a function of the ratio of spins that you flipped, which goes from 0 to 1/2. And so again, here, well, you have one aspect that stands out, which is the growth of the Lyapunov with n, which it's usually happens with this sort of systems. But you definitely see a region. I mean, we'll try to be a bit more precise about this. But for a given n, at least, you see a region where the Lyapunov is small, and then it can start shooting up. Okay. And so here I'm just showing that the numerics that indicate that for this relatively high number of flips, you still have this fast scrambling behavior. So these start scaling as log n. But perhaps what's more interesting I mean, in this case, it's hard to do this analysis because there are a lot of fluctuations. But what we looked at is, these curves as n increases, which is from green to yellow, they seem to move to the left, right? And so we looked at, basically roughly define, what's the critical value of k over n, where the Lyapunov has the higher derivative or something like that. And you get a nice fit of basically k over n behaving as 1 over the square root of n, which means that you start getting scrambling when the number of flips is roughly root n. These are what, sorry? These are, I mean, there's no temperature involved here because the only thing, so these are classical, yeah, and you need to just specify the spin coordinates of each particle. So everything is our spins pointing along the x-axis, but it could be all of them or it could be alternating. K is the number of flips that you produce. All right, so that's nice.
It's not the Lyapunov problem like footballs. It's a different argument.
Yeah, but I mean, because of this, so again, we cannot calculate this for very large n for the quantum case. But there's, yeah, I mean, you can make an argument that this, it sort of proves the same quantity, but in the classical regime. All right. So this is perhaps a bad idea to leave this for the end, but okay, so I've shown you a couple of results showing kind of how you change the initial state, you change from this collective to scrambling behavior, and we saw basically this in terms of, okay, how many flips would you need for each n to go from one to the other? So there's another argument that you can make, which leads to a very nice mathematical analysis. The origin of the argument is a bit hand-wavy, unfortunately, but bear with me and I'll try to explain it. So this was a question that was posed in a different sort of community, particularly people who are trying to generate spin squeezing with connectivity that wasn't all-to-all, because that was very hard to get. And so they were asking, how, given a connectivity graph, how well does this collective dynamics, is this collective dynamics preserved? So I can hope that I can get these spin squeeze states. And so the argument that they developed actually in this paper goes like this. So if I take the XY Hamiltonian, and I can always rewrite it like this. So the idea is that this is going to be a generalized one-axis twisting, okay, which they call the GOAT, which is a nice kind of acronym to have, I guess, for Hamiltonian. So the one-axis twisting Hamiltonian is the generalized. And then it has a term, which is the Heisenberg model on that graph, but this term also commutes with J squared. So it's generalized in the sense that this Hamiltonian still commutes with J squared, so it perfectly preserves the collective order. And now what I have is then this other term, which is a perturbation, which again, roughly speaking, you could say, well, it's measuring, however many bonds are missing, right, from the all-to-all connectivity. And the important thing is that this does not commute with J squared anymore. So this is the part that breaks the conservation of J squared. Does that make sense? And so the argument is, okay, let's look at what's the gap, like the energy difference between the collective subspace, which did I write? Yes. So a collective subspace, which is the one that has this maximum spin, with the next one, so the minimum gap of that, to see, given a strength of the perturbation, which I cannot control, it's just there, how resistant will the Hamiltonian be to the presence of the perturbation. So the idea being, if I calculate this gap, and the gap, for example, goes to 0 for large system sizes, then you're screwed, because any perturbation that you introduce eventually is going to kill the collective order. But if it remains constant, or even if it grows, well, you get this protection from the gap. And so you can do this very straightforward, in a very straightforward way, in the easiest, in the most straightforward case, which is you only consider this Hamiltonian, right? Again, this also commutes with J squared, so the eigenvalues only depends on JC, so it doesn't affect. So I can say, okay, the ground state is all spins pointing up, and I want to see what's the first excitation or the first excited state. And because this commutes with the total magnetization, I can look at this for each magnetization sector. And you get this result, which perhaps you were aware of, but I wasn't when I started looking at this, is that if you write, the Hamiltonian of the XY model in the single excitation subspace, you basically get that the Hamiltonian just relates to properties of the graph, which perhaps unsurprising, but the Hamiltonian is basically equal to the Laplacian of the graph, right? So the Laplacian is given a graph, you calculate the degree matrix. So for each node, how many edges it has sticking out, and the adjacency matrix you subtract. That's the Laplacian. So, I mean, that's kind of an interesting connection, but we are not really using it. It's interesting because if you have a network with positive edges, then the Laplacian is the generator of a classical random walk. So you can relate this gap to a kind of a dynamical thing, but we can come back to that after. This is just a way to calculate a metric that should tell you how protected these things are. So we did that before for these different graphs. And so you get, I mean, you get results which are consistent with the numerics, in the sense that there are some graphs which leads to a gap that decreases with n, and there are some gaps which are constant or increase with n. And the ones that are constant or increase are the ones in which we find, for example, this generation of GAC state, for example, the powers of 2, the hypercube of the all-to-all, while the ones that have a gap that decrease are the ones, for example, the nearest neighbor, or, sorry, I didn't write this. This is a power law system with an exponent of 2. So system that, even though are all-to-all, they have, the interactions decay too rapidly. They have the same behavior. So does this make sense? I mean, it's a bit convoluted in a sense, but for now you can follow me just in the sense that we are calculating this delta, and we're taking this as a measure of how well this graph will preserve states in this subspace. Now the problem is that I said, I'm calculating the gap from the maximum J to the next one. But when I start doing spin flips, I don't have maximum J anymore. Right? If you do a spin flip, it's not true that J squared is anywhere 2. So you're actually climbing down the ladder of J squared. And so this is annoying, because it means that, okay, maybe what I need to do is I need to look at gaps between excited states now of the Heisenberg model, which are a bit more annoying to construct. But what we did instead is we took this approach in which we basically we still do the same sort of analysis, because we said the following thing. So now we're interested in states that have these K spin flips, right? So with respect to the reference state, this plus, I'm doing a number of flips, and these alphas are just indexing where I'm flipping. And so the state that I now care about is this thing. But or however you want to call it. And you can think my original Hamiltonian on a flip state. I could think about flipping the state that comes from a different state. And you do that by defining this transform Hamiltonian here. So you just take this transformation, which is a bunch of spin flips, and you apply it to a Hamiltonian. And because the Hamiltonian, has this very structured form, this just means you're changing the graph, or you're transforming the graph. So it's easy to see that when you do flips, for example, if I flip on side L, then that means that all the row L and column L of the adjacency matrix will get a -1. And so now I have an adjacency matrix which has been transformed. Now the state that you get is not the same, but it's the same up to local operations. So for example, if we want to think about how much entanglement is being built, these two states should be comparable. But what's interesting is that I don't need to change anything in the analysis. The only thing I need to do is for each choice of spin flips that I do, I transform my adjacency graph such that it has the same connectivity, but now it has some negative edges. So if my adjacency matrix has negative edges, it doesn't matter for the argument that I made before. You are still interested in how big is the gap between the collective subspace and the one that's closer in energy. And so that's what we analyze. So we analyze what's this gap for different system sizes as a function of how many flips I do. Again, these are this model of alternating flips. And so what you get is that eventually you do for this case, this is 0 flips. The gap should be 4. This is what we calculated before. This is the collective case. But as you start flipping spins, then at some point it happens that these gaps plummet. And again, what we see is that the value at which they plummet, they move to the left, and we get numerically the same analysis, the same scaling that we got for the Lyapunov, which is nice. So at least for this sort of protocol, you get that you can basically flip at most root and spins and sort of maintain the collective behaviors to some extent, and then after that, you start seeing this scrambling behavior. Okay, that's pretty much it. So yeah, I mean, what I wanted to share is this problem that we've been thinking about. I mean, really how this came about was when I joined, we studied this model of how to generate spin squeeze in a GHZ state. And then I knew that people in the group had worked with this powers of 2 model, but I never realized it was exactly the same model. And so when we realized that, we said, I mean, there should be a way of explaining how these two things are connected. And so we are doing efforts towards that. I find it interesting is within kind of the appeal of these models that there is no randomness. The model is just one. It's very quirky, but it's just one, and you don't really need to change any parameters in the model to see this different behavior. You just need to change the initial state. So, for example, in the original experiment by Monica Shai-Smith, this could be brought naturally because you just need to change the initial configuration. Is the exact same Hamiltonian. And so we're building this quantum and semiclassical and sort of graph theoretical arguments to paint a picture of what's going on. Crucially, trying to, go to high system sizes to understand really what's going on for very large. So perhaps some interesting things that pop up along the way as we've been talking about this is there have been a few papers in the last couple of months on many-body classical chaos, which I don't really understand, but So this one by the group of Roig-Mosner is about how many-body chaos emerges from the presence of quasi-particles. So it's basically also about kind of a Heisenberg Hamiltonian where at short times you get this description that, or for some initial states, you get this description that is governed by spin waves. But it's just as you start to add impurities, which is a difference in the initial state, as far as I understand it, you start to get, as time goes by, a transition to chaos, which was shown in the rest of the picture. So I thought this was perhaps on the similar vein as, change the initial state instead of changing the model. This I'm very curious about. I don't know if anyone has come across this. So the connection of the gap with classical random walks really only works, as far as I understand, if your graphs do not have sign, like if the edges are all of the same sign, are all positive. The moment you have positive and negative edges, you lose the direct kind of interpretation because probability is no longer conserved. But people that work on networks think about how you would define a random walk in a sign. And so these are all, the moment we do a flip, we suddenly have a sign graph, and it would be interesting to see if we could connect these two things. And a little bit about what I said in terms of the experimental implementation. One version of this model has already been experimentally implemented. And this would amount to kind of looking at different initial states to see different behaviors. Just quickly flash, as I was saying, some other research interests. If people, see this and say, "Oh, this might be interesting," or "I'm interested in that too," I'm keen to have a chat. So the other thing that I do is quantum control and optimal control. That's what I did in my PhD, and I'm kind of going back to it. And we have this result on how to achieve using control evolutions which are robust to any perturbation, which we are trying to still understand more. This whole business of scrambling in terms of operator growth, I'm always interested in how you can get effective descriptions for this operator size distribution, which would be like a more refined version of just the size of the operator, because you could look at variance and other things. And in general, we've looked at, we've been looking at what happens in spin ensembles or spin with long-range systems, with long-range interactions, in the presence of measurement, or, with these applications for sensing, or some algorithms to treat long but not super long interactions efficiently numerically. Right, and that's pretty much it. Just want to flash a picture of my collaborators. Sridevi is really the one that did most of the numerics and most of the heavy lifting for this work. And as I said, the methodology aspect of the project was published last year, and we're working on this second bit. Yeah, thank you.
If you look at, if you take this polarized state and look at, for example, this overlapping eigenstate.
Yeah. Yes, this is one. So up to the system sizes that we can do, this is what it looks like. So this is the spectrum of the powers of 2 Hamiltonian for n equals 12. And these are the energies, and these are the spin numbers. So the line is the maximum one, and then it starts to decrease. So for all to all, these would all be like perfect lines here because of these. And so what we see here, again, we can go so far, but we definitely see, the zero excitations.
It has almost all this overlap with
J, absolutely, yeah. And this is something that it has to be looked at for this model, but there's, Alessio Leros and Silva Papalari, they studied this problem for power law decay in the concept of scars. But this is not a chaotic. This it has symmetry, so it doesn't really look like the typical chaotic spectrum. But for the case where you have an external field, where you do have that, then they were basically seeing that the collective states have very good overlap with the maximum J, and then it starts increasing.
I guess it's easy to construct if you do just take Hamiltonian project into the another two sectors that.
Well, I mean, one thing, so this is exactly this our paper here. Maybe I have a slide actually. Sorry. Yes. So yeah, so basically we worked with the people in UNM